Usually I'm working a different research field from nanoscience. My major focus is on the magnetism or the magnetic resonance techniques. So the reason why I am here is that recently we are particularly interested in the measurement method using MEMS device. One motivation is that we want to measure the small crystal sample. In condensed matter research, the measurement of the single crystal sample is important, but single crystal of newly found material is always very small. So we need much higher sensitivity than the commercial squid magnetometer. This is the most popular and standard magnetometer in the world. In such case, the torque magnetometry using the MEMS device, in this case, this example is a piezoresistive cantilever. This method is very suitable in a simple measurement setup, and we can achieve much higher sensitivity. And in this method, we measure the magnetization by measuring cantilever deflection caused by the magnetic torque. In addition to its very high sensitivity, another advantage is that this method can be used at very high magnetic field and at low temperature. So this piezoresistive cantilever has been used to investigate the interesting magnetic field-induced phenomena, or sometimes it has been used to measure the Hertz-van-Alphen oscillation. This is quantum oscillation of the magnetization. This measurement was done to investigate the K-space property, Fermi surface of the metals or superconductors. And also, we have another motivation. We study magnetic material using the magnetic resonance techniques. In our case, electron spin resonance. This is a powerful spectroscopic method to study the local structure or the electronic state in solid. The ESR spectrometer is commercially available in microwave region, but we want to perform this experiment at very high frequency range. In the ESR study of the novel magnetic material, we need terahertz frequency. But we have a problem. As electromagnetic wave frequency increases, the power of the light source decreases. So it causes degradation of the sensitivity. So we need to enhance the sensitivity by enhancing the detection sensitivity. In that purpose, we use the mechanical sensor, and this can achieve much higher sensitivity than conventional method in this frequency range. The principle is simple. This is the ESR-induced magnetization change. This magnetization change occurs due to the spin flip transition of electrons. So ESR induces a spin flip transition, and it changes the occupancies of these spin states, so it affects the macroscopic magnetization. So for such purposes, this piezoresistive cantilever has been used, and this was a really popular tool because in addition to its very high sensitivity, this was very easy to handle. And these points are important for us, material physicists, because we are not the MEMS experts, so we don't have our own fabrication facilities, so we need to buy the commercial products from manufacturer. But unfortunately, this cantilever was discontinued from its production in 2014. So after that, we were looking for the alternative device. And last year, we came to know that there is a smell sensor, MSS, and this is also a piezoresistive mechanical sensor. So soon after we saw this device, we were sure that it can be used as a tool for magnetometry. Then we tried. Before that, I should explain this chip. This is a commercial chip of MSS, available from NanoWorld. And this has a circular silicon membrane here. Diameter is about 1 millimeter, and thickness is about 5 micrometers. And we define, and this membrane is supported by the piezoresistive bridge, 4 piezoresistive bridge. And we define each piezoresistor as P1 to P4. But in this measurement, we use only P1 and P3, and P2 and P4 becomes inactive after we removed the wire here and short the path here. And by doing this, we can push the electric current through only P1 and P3. P2 and P4 becomes inactive by this configuration, but this is not a problem because P2 and P4 is in this symmetrical line, stage rotation axis. So we detect the twisting motion of the membrane caused by magnetic torque using these 2 piezoresistors. When the magnetic torque is exerted on the sample, this piezoresistive change is subject to the deflection. When the P3 is pulled downward, P1 is pulled upward. So piezoresistance change is detected by forming a bridge circuit with external resistors, and the voltage signal is written as this. Here, this configuration might seem to be a little tricky, but it's important to cancel out the magnetoresistance effect. On the other hand, torque component is enhanced by a factor of 2, so we can extract the resistance change only due to the magnetic torque. Let me show some example. We measured 2 superconducting samples as a test sample. The left figure shows the data for layered organic superconductors whose transition temperature is about 10 Kelvin. And the sample has a platelet shape, and the sample dimension is here. And the sample C-axis is in this direction, in the direction same direction as the normal of the membrane surface. And this is the data. We can observe the hysteresis curve. This is a typical behavior due to the vortex spinning in the type 2 superconductors. And here we define this angle as a angle between the sample's C-axis and the magnetic field direction. As angle rotates, this hysteresis becomes large, and at the same time, the magnetic field at which these 2 lines merges shifts to the higher field. These are characteristic behaviors for the layered superconductors. And the right figure shows the quantum oscillation effect of strontium ruthenate. This is also a layered superconductor, but at this temperature, this sample is still in the normal state. This oscillation period corresponds to the K-space property of the sample. And by extracting the oscillation frequency as a function of the angle between C-axis and field direction, we can know the shape of the Fermi surface. The data is well fitted by an ideal case for 2-dimensional substance. So this is consistent with this is a layered superconductors. In general, quantum oscillation measurement is not easy, but so this means that the torque magnetometry using MSS has very high sensitivity. And we also applied this technique to the ESR measurement of cobalt taton salt. We used this compound because it has relatively high spin density, and it also has magnetic anisotropy. The magnetic ion of this substance is cobalt 2+, located at the center of this octahedra. And as you can see, there are two inequivalent sites, cobalt 1 and cobalt 2. These are origin of two peaks in the ESR spectrum. And as angle between the symmetry axis and the magnetic field direction rotates, we observe the G shift along this line. The spin sensitivity was estimated to be around this value. Actually, this is 1 or 2 orders smaller than the microcantilever, but in any case, this is the first data of ESR spectrum obtained using MSS. And finally, I want to briefly show the more recent experiment. After the MSS, we started to use a much thinner membrane. This is also commercially available membrane, but the material is a little different. This is a silicon nitride membrane. The thickness is much thinner, 100 nanometers. But although this chip has piezoresistive readout, but in this chip, the piezoresistive circuit is not embedded, so we need the optical detection method. But using this method, we successfully obtained the ESR spectrum at very high magnetic field. We succeeded in this technique up to 15 Tesla. So this is also a promising technique of high frequency electron spin resonance measurement. Sorry for I went over time, but I should conclude. The conclusion is simple. MSS can be a good tool for magnetometry, and silicon nitride nanomembrane can also work as a high frequency ESR detector. So this shows that membrane type device will be a promising tool for the magnetic measurement. Thank you.